SwayamPrabha. Digital India. Educated India.
So hello and welcome back to another lecture on Introduction to Soft Matter. Today what we are going to do is we are going to look at some example problems. These example problems have been designed so that we can actually end up revising some of the materials that we have been discussing. So it will be a very good work through some of the important concepts that we have already discussed, right. So let us take a look at another problem, number 2. Okay, so the question we have is that for a strain history, so the strain history is given to you as, okay, here I am just going to use S again, but please remember that this is not a Laplace transform variable, but this is since we are going to use time in so many places, so this is just variable represents time. So we have epsilon naught into sine omega s. So we have a sinusoidally varying strain. Okay. And the question is, for this given strain history, calculate the work done per cycle. So now let us try to solve this particular problem. So this is given to us as the input, and recollecting from the material that we have already discussed for sinusoidal strains and sinusoidal stresses, is that this input will create an output in the strain, for the stress, which is also going to vary in time. But now the expression for this will be given by epsilon naught g dash of omega sine omega s plus g double dash omega cosine of omega s. And once again, g dash and g double dash have the same meanings that we have used in the class before, right. So we are already familiar with these variables. Okay. So now the work done on a material per unit volume is given by the integral sigma into del epsilon. This is basically the, this looks like the force into displacement form, right, and we are integrating over the entire strain produced in the system. But our question is to find out the work done per cycle. So it means per cycle of this sinusoidal input. So we would like to be able to integrate this in time. Okay. So if you want to now find out the work done over a time interval, over a specified time interval, then my W will now become this integral over that time integral. So let us say that that time interval is, so my work will now be, has to be integrated where the limits are this time interval. So let us say this is some time t and then till 1 unit cycle. Okay. So, t here represents the time period. So, this is sigma del epsilon. Now, I want to integrate this over time, but so I would like this integral to be such that this integration can be easily performed, right. So, what I will do is you can change the integral to this particular form, where s represents a time variable. Okay. And let me also clarify that where, okay, let us use it right here, where t is the initial time and capital T is the time period. Time period of the sinusoidal oscillation or the input, right, such that so t is basically equal to 2 pi by omega. Omega is the frequency of the input, and without loss of generality, because I am interested in integrating this over a cycle without this any loss of generality, we can set this small t to 0. Okay. Okay. Now, this particular form d epsilon by ds should already be known to us, because the input is known to us. So, d epsilon by ds, because the input is known, is simply epsilon naught into omega into cosine of omega s. But we also know sigma as a function of time, right, because we have written it down here. Okay. So, for this integral, both these two terms are known to us. So, we can write down the expression for work as an integral, but this time I am going to set the small t as 0. So, this is just 0 to capital T once again being the time period of oscillations. And here I will have, if you multiply all of these, you will have omega epsilon naught square g dash sine omega s plus g double dash into cosine of omega s, and there is one more cosine here. ds. Okay. So, we have to evaluate this particular function. Okay. So, let us just bring this inside this cosine, and we see that basically what we have to do is we have to, there are two terms that are contributing. Okay, sorry, this is g dash of omega. So, let us be consistent. Okay, sine omega s into cosine of omega s plus g double dash cosine square omega s ds. Now, we are going to perform the algebra in a second, but you can actually already anticipate the answer by just looking at this particular form. Now, see here what we have is a sine omega s into cosine omega s, and if you know your trigonometry well, you know that when we integrate this over one time period, this term will actually have to vanish. But here is a term where we have g dash, okay, I think I have left out the omega, sorry, and multiplied by a cosine square. Now, over a time period, the cosine square, obviously because it is a square, it is always positive, and you have g dash. So, this term will not vanish, but the term associated with g dash will actually vanish. So, in the work done, only G double dash will be contributing, and you can see that without even doing the full algebra, right. But let us go through this set of calculations. Now, observe that the DDS of sine square omega s is actually given as 2 omega sine omega s cosine omega s. This inspires us to actually replace this particular term with this derivative term. So now my work done is again integral 0 to t, you have omega epsilon naught square by g dash of omega divided by 2 omega dds of sine square omega s plus the other term is obviously there, g double dash of omega, we have cosine of cosine square omega s ds. Now, when we integrate this term, these are all constants with respect to time. This is the only function here which is this is the only variable which is a function of time, right. So, my integration actually becomes rather straightforward, because all these other terms which are independent of time I can simply bring out, and when you integrate this you will be left with sine square omega s, and this has to be evaluated over one time period, plus this particular term over here, which again I will write the constants outside, t, and I suggest that using a trigonometric identities we convert this to this particular form. Now, note that this particular function, if you go ahead and evaluate it over a time period, actually results, the answer comes out to be 0. And for this other functional form, if you evaluate that one, 0 to t 1 plus cosine of 2 omega s by 2, you can show that this should come out to be pi by omega. Okay. There is a ds missing here, and that should be rather easy to see, right, because when you integrate this first part you will get a linear term, and then this is again a sinusoidally varying term which will basically cancel out. So, if you use these and reevaluate the work done term, then that comes out to be simply epsilon naught square, this is epsilon naught by the way, that comes out to be epsilon naught square omega g double dash into pi by omega, or basically this 2 omegas will cancel and you have pi epsilon naught square. Okay. So, this is our answer that we are seeking right here. So, as when we had started out with the problem and we had not even finished the full integration, we had already said just by using our trigonometric understanding of trigonometry that this first term is going to drop out and the second term is the one which is going to contribute to the work done, right. and surely that is what we see. We only have the g double dash term here, and the g dash term does not come. Now, also notice that there is no explicit dependence on omega in here, but the dependence on omega is contained in the dependence of g double dash on omega. The other important thing is that in the very beginning, when we had discussed sinusoidal oscillations and work done, then we had said that the work done on a solid body is fully recoverable, right. That is what the pure elastic or a classical elastic solid is supposed to do. When you do work on it over a sinusoidal cycle like this, it is the work done is fully recoverable. So, in a given cycle there is no net work done, whereas in a fluid there will be work done in a cycle, and that work done is eventually going to be dissipated in terms of in the form of heat. And the final expression that we have found just suggests just that the storage modulus does not contribute to the work done in a sinusoidal cycle, but it is only the loss modulus which is important, which means that loss modulus, now you can see that the naming is so appropriate. When we say g double dash is the loss modulus, you can see there is one more motivation of calling it that this work done that is done over a one time period is now going to be lost in terms of heat, right. So, overall this satisfies our intuitive understanding of the viscoelastic materials also very nicely. And also please remember that these are again limited to the class of the linear viscoelasticity that we had all these. So, all the assumptions that we had already used in coming up with these expressions to begin with still apply here. Okay. Okay, so, with that we are done with our second problem, and we move on to one more, a third problem that we will do. I will write down an expression, and the task is to figure out if the expression is correct. Okay. So, evaluate whether the following relationship is possible. And the expression is g double dash of omega is equal to minus integral 0 to infinity d ds of delta g s sin omega s ds. Okay. So, to figure this out whether this expression is indeed correct or not, we will go through the process we have sort of seen before. So, we have seen before, or we have seen earlier, that for an input, a sinusoidal input, epsilon s is equal to epsilon naught sine of omega s. When you apply that, then you end up getting an expression for the loss modulus as omega times 0 to infinity delta g s cosine of omega s ds. Okay. This is something that we have already seen before. So, in a sense we are asking whether this particular integral is the same as this particular integral over here. So, to evaluate this, let us go back to our basics, and we will write down the expressions for the stress that we had found. And we know that the stress can be written as this particular function form if the stress relaxation function is known. and this is equivalent to integral 0 to t, where you can switch between these two terms. So, okay, let us use this formulation. Okay. And we already know that in order to get an expression for G double dash, we had assumed a particular form for the stress relaxation function. So, we will assume that GT, okay, sorry, we will assume that GT can be written as some G infinity plus delta G T, where the second part decreases to 0 as time goes to infinity. Now, so using this particular expression here, so we have already said we will use this particular formulation. When you insert this over here, the derivative will only account for the second term. Right. So, the derivative of GT will only involve the delta G, right, and not involve G infinity. So, we can write sigma t is equal to G0 epsilon t plus integral 0 to t ds So, what is it that we are really looking for here? Now, the strain is the input, right, and we are trying to figure out the expression for the stress from this, given that you know the functional form for the stress relaxation function. So, we now have to assume some form of time dependence for our strain here, which you can take it as either as sin omega s or a cosine, but for generality what we will do is we will just go into the complex formulation. Okay. That just makes life easier for us. Okay. So, to check generality, we will use the complex formulation, which means we will use epsilon t as some epsilon naught e to the power I omega t, right. So, let us go ahead and replace that in the above expression. So, that implies that my stress, which is the output here, becomes epsilon naught e to the power I omega t G0 plus integral 0 to t, and it is the same, first term remains the same. And now, for epsilon t minus s, we have to write minus I omega s ds. It is t minus s here, but I have already taken this e to the power I omega t out. So, that takes care of that. And we had stated earlier that delta GT is such a function that it goes to 0 as t goes to infinity. So, basically this functional form has to be such that this is g t with respect to time, that this thing decays over time, and this is basically a g infinity here, by the way. Now, if this functional form is valid for the stress relaxation function, then you can make an additional observation, and that observation is that g, the derivative of this also goes to 0 as time goes to infinity. Now, you are also to make an additional you have to make an additional assumption that these integrals will converge when we take the limit of t tending to infinity, but assuming that the integrals will converge, we have made certain assumptions about the functional form of the stress relaxation function. The reason we are making these assumptions is because we are going to look at a system where the transients have died out, and we will look at the long term time limit, which is very similar to the formulation that we carried out in the class earlier. So, we are going to do this integration such that this 0 to t, this t will be replaced by infinity, right. In that case, assuming that all the integrals do converge, okay, so that assumption is also there. I am not writing it down explicitly, but in the long time scale where all the transients have died down, I should be able to write, if the integrals converge, I should be able to write down the output, which is the stress, as, so after transients have died out, I should be able to write my stress as some complex modulus multiplied by my input, right, such that this complex modulus only depends upon omega and not on time. So, basically what we are saying is that this g star is equivalent to this particular form right over here, such that the integration is now going to be performed over 0 to infinity. This is, by the way, very similar to the thing to the formulation we had performed in the class. Okay. So, our g star omega is equal to g naught g 0 plus an integral, and the integral is just the same as before, dds of delta g s e to the power minus I omega s ds. But now you are going to perform it, this integration from 0 to infinity. So, this implies that we already know that the complex modulus is basically the storage modulus plus I times the loss modulus, right. So, I can write down my g dash of omega as being equal to g 0 plus integral 0 to infinity dds. This form simply remains, and for the real part I have to take the cosine omega s, right, cosine omega, sorry, omega s ds. And similarly, just by comparison, you know that the g double dash can be written as minus 0 to infinity dds of the delta GS I do not know this particular form because this delta G has not been given to me. Okay, so we will leave it at this, but this is exactly what we are after, right. So, if you remember the original question, we had asked if this particular functional form is possible, and what we did is we have already been familiar with one of the functional forms, but we went ahead and we chose a different representation for our stress, and we carried out the exact same sequence of steps that we had carried out in the class before for getting our evaluating our complex modulus. And when you do the same set of steps, just because you chose a different expression for sigma t to begin with, you will end up with this particular expression, which we know is equivalent to the other representation as well. So, we know that this relationship is valid, and we also know the conditions under which this is valid, right. Okay. So, the purpose of this particular exercise was to show you that there are different forms of G dash and G double dash that can be written, and it's just because if you encounter a different form, you should not get confused and think that it is incorrect. Okay. So, with that we have ended our problem 3.